Again, we still have some time for the last talk of this session. We have Ambroise Fleury from, I think it's CEA. Yes, from CEA. And he will talk about some alternative seeding strategies for the number VC.
Thank you for the introduction. Hello, everyone. So today I'm going to talk about factorization. I'll start by talking about why factorization is important in cryptography. Then I'll talk about the number VC, and finally our contribution to the NFS, which is the implementation of the number VC algorithm. So I'm sure you're all very familiar with the Asiacrypt system. So let me do a quick recap. You have each user has a private key and a public key. The private key is used for decryption and is generated from two random prime numbers P and Q. And the public key used for encryption is the product PQ, which is N. So the security of this crypto system is directly linked to the oddness of the integer factorization, as if you can find P and Q from N, you can basically find the private key from the public key, which breaks its. So the generic factorization method I'm going to show you there is used is the basis for large integer factorization. And basically, it starts by the goal is to find square congruence of square like that. So if you have x squared equal to y squared mod n, the nx is different than y, then thanks to this, GTD gives a factor of n. Now the question is how do we find this congruence? Dixon's factorization method is built upon this, and we build the square by generating many y's, small y's, such that we get such that they are all equal to a square x mod n. If a small y is smooth, which means it has only small sizes, it is called a relation. We can use relation to build big y squared mod n as a product of small y. So basically there are two parts. The first one is the relation collection, where we generate many y's and find many relations, as many as we can. And then the second step is the linear algebra, where we combine the relations into a square, and which leads us to this square, this congruence of squares. So the important idea is that we go from factoring a large number, n, to factoring many small numbers, small y's. Relations look a bit like this. In this example, we have a tiny factor base that is prime numbers up to 17, and we have a few examples of small y's and their factorization there. So we can write them in this way, such that the next step is to combine them into a square. It's pretty easy, as you just have to combine lines to get even exponents on each column, which means the result is a square. Now I'm going to talk about the number filsive. This is built upon what I just showed you, but it's a bit more complex. First of all, Cadeau NFS is an implementation of the NFS. It is open source and it can also compute discrete logarithms, although I'm not going to go into details about that. In 2019, it beats the factorization record with the factorization of RSA with 240 digits. And a few months after that, it beats its own record with the 250 digits number, which is the record, the current record. Its computing time is dominated by relation collection. As you can see in the table below, the relation collection is approximately 10 times, approximately 10 times as much as the linear algebra part. And that is true for both records. So to speed up the LONFS, we chose the relation collection part. This about the relations in the number field sieve, they are a bit different than the relations I showed you earlier. So I'm not going to go into too much detail about about the mathematical background of the number field sieve, but there are two sides, and we play with pairs AB of coprime and small integers. And basically, we have two polynomials, and for each pair AB, we have two norms. One norm on the side 0, which we call the rational side, and one norm on the side 1, which we call the algebraic side. This is what the polynomials look like. Those were chosen in the 250 record. So to a quick recap, so we go from 80 pairs, of which we can have as many as we want, and we compute the norm on the rational side and the norm on the algebraic side. And in the case, so for one pair AB, in the case where this norm, this rational norm is smooth, and as well as its algebraic norm, then we call that a relation. And that is the goal really is to get as many relations as possible. So how do we go into factoring norms to get actual relations? So we have two methods. So for each side, each pair AB and each norm, we use two methods. The first one is sieving to find small and medium factors. And the second one is the elliptic curve method, ECM, to find large ones. So this looks like this. For instance, on the rational side factor, prime below that parameter are recovered thanks to the sieve, and prime above that are recovered with ECM. This is the same on the algebraic side with different parameters. So the first step is to sieve all norms thanks to the structure of the AB pairs, and the second step is to use ECM only on the most promising norms, only on norms most likely to become relations, and explain a bit later what that exactly means. This is what sieving looks like. So for each prime number P, we sieve all its multiples along the A and D axis. So we take every AB pair, which norm we know is a multiple of P. So promising pairs. These are the best candidates to give a relation. So sieving, we start by sieving. This is the number of bits of a norm, and we are trying to find all of its factors until we get one. We start by sieving, And if we are unlucky, sieving will find only so many factors, and we will filter the norm. In the best case scenario, we find enough factors, and we call that a promising norm, which means we will keep it and send it to the ECM to find the remaining factors. The bound, the promising bound, is a bit tricky to choose, because if it is too high, many pairs of low quality will be brought to ECM, and it will take too much time. However, if it is too low, then we will have few pairs of high quality, which will give too few relations, and we will need to receive some more areas to get enough relations at the end. Now, let me talk about our contribution. So, to improve the relation collection in LNFS, we try to get as many promising pairs as we could in at a much lower cost. And for that, we picked the small sieve. So it's a subroutine of LNFS sieving, which is only focused, which only finds small primes. So small factors are worth few bits, and we found they are not decisive on promising pairs, which means medium sieve might be enough to decide whether or not a pair will be promising. So our intuition was to remove the small sieve and replace it with different subroutine. Well, still get very small factors. Batch factoring is a factoring algorithm by Bernstein. It takes its input is a list of integers and factor base prime numbers. Its output for each integers its smooth part, which is basically all of its factors from the factor base. So this factorizes a set of integers. Is the important idea. And we propose this hybrid version. So we pick an intermediate batch promising bound, which is larger than the ECM bound. And then we start, the first step is to sieve only on medium primes. The second step is to remove non-promising pairs. So we filter the first time. Then we get the small factors using batch factoring. Then we remove non-promising pairs again. So we filter a second time. And then we get finally large factors with ECM. And this gives us relations. So to compare both versions, on the original version, we use the sieve to recover factors below lim and ECM above. On our hybrid version, we use sieving to recover factors below lim but above the batch bound, and factors below that are recovered thanks to the batch factoring algorithm. And so that gives us, as before, we have the number of bits of a specific norm, and we're trying to find all factors and get it to one. If we are unlucky after the sieve, after the partial sieve, we do not find enough factors, so we remove it. If we are, then we get the promising norm. We get it to the batch factoring, and we have another step of filtering. If the batch does not find enough factors, we remove it. If not, if it finds enough, then we have a promising. So we have two filters which improve, which speed up the seedings. About the implementation in NFS, so we have access to the RSA 250 relation, so from the record. So these data allowed us to target specific numbers of relation. Also, it allowed us to test parameters, and it was a good benchmark baseline. The benchmarks were done on sampled seed regions, so we picked seed regions at random, and we compared, we tried to find the best parameters and to compare it to the original algorithm. Also, it allowed us to extrapolate pretty easily, since it's a parallel algorithm. So on just a few regions, you can have a pretty good benchmarks. Our results are a few of our results. So we picked a few example areas. The first one is here. We, on the original version of this, on this specific area, we found 390 relations in about 1800 seconds. And our hybrid version found less relations, 347, however, in much less time, 6900 seconds. So we found fewer relations, but speed up contracts this, and in the end, we get about 10% speed up locally in this area. So in the second example, it's about the same. In the end, we get a local speed up that is very similar. So this leads us to believe this hybrid version could be used to help beat the next actualization record. Thank you very much for your attention.
Thank you very much for the talk. Is there any question?
Thanks for the talk. So, what does this speed up mean for the overall factorization algorithm? Do you have an idea? So before we had this 800 CPU meters for the entire algorithm, right? And now we speed up a part. How much does this mean?
Well, so we have a local speed up, but we found we still have to compensate the relations we don't find. So yeah, we kind of have to search wider, and that might take a bit more time. So that's why it's a local speed up and not a global speed up. But we're not very sure, and we should do the benchmarking in the future.
Other question? Yes.
Question. I want what is the batch?
What do you mean?
Batch.
Batch is the batch bounds. That's this is those bounds. So we have a bound here for partial sieve, and it's a new bound. And so if we move it, we can move it to the left and or to the right, and it means we filter more or less norms. And so we have to slide it to the optimal place. So as we get enough promising norms, but not too many. Is it? It is. Didn't understand.
I can use on
Okay.
Other question? I might have some. So, if my understanding is correct, the parameters were adjusted experimentally or also from existing experimental data from the open competition, right?
Both. So we have a few parameters. We have those bounds. We also had to try which primes we had to cut. So which primes we should cut the sieving part, and so we found some parameters thanks to the data from the records, but also some thanks to our implementations.
Okay. Would there be any hope to try to have a heuristic, maybe understanding formally of where the threshold would be for a given size of an unearthed factor?
I feel like in the NFS, it's like there are so many different breaks. It's just implementation.
I see. Okay. And so then probably it's the same answer for my next question, which would be, could we imagine that we can extrapolate on a smaller factoring results to have an idea of what we could choose in advance for larger computations, or do you think it's
But it's not straightforward. You have to try in as much for their records. So yeah, 240 and 250, a lot of parameters, which just fit experimentally.
okay? Thank you. Well, if there are no other questions, let's thank our very efficient speakers for this afternoon again. This is it for this session, I think, and so I guess we meet at the coffee session.